Chapter 4, Entropy, Section 4.5, the Second Law of Thermodynamics. The second law of thermodynamics states that the entropy of an isolated system can never decrease. Therefore, any process that's associated with the entropy increase of an isolated system is irreversible, because such a reversal would result in the entropy decrease of an isolated system, and that's a violation to the second law. The universe is considered an isolated system, and therefore the entropy of the universe can never decrease. And we can also use this mathematical inequality here. The change of the entropy of the universe can never be negative. It has to be positive or zero. The entropy of an isolated system always increases, except for two scenarios. Scenario 1, this system has reached thermodynamic equilibrium. That means its entropy can no longer be changed. It has been maximized. Scenario number 2, this isolated system undergoes a reversible process. For example, reversible adiabatic expansion. In this case, dq reversible is 0. And remember, in thermodynamics, ds is equal to dq reversible over 0. So if dq reversible is 0 itself, ds is 0, delta S is 0. So in this scenario, entropy is a constant. Again, we have these two different scenarios. Scenario number 1, the system has reached thermodynamic equilibrium. The entropy has been maximized. Scenario 2, it's reversible adiabatic for this isolated system, and then the entropy remains unchanged. Now let's look at one example problem, 4.5.1. Calculate the entropy change of the universe when 1 mole water freezes at temperature T, and T is lower than 0 degrees Celsius by an infinitesimal amount under 1 atm pressure. We may assume this T surroundings is equal to T, so both of these are actually, you can say 0 degrees Celsius, or you can say, well, it's lower than 0 degrees Celsius by an infinitesimal amount. Alright, and then we can assume dq is equal to dq reversible, because for such a process we may consider this process is reversible. Alright, so by looking at this reversible, you might think, well, then this delta S universe has to be 0. It's correct. Now let's look at delta S and delta S surroundings individually. So first, ds is dq reversible over T. That's the definition. And 2, if dq is equal to dq reversible, we have this dq over T as the expression of ds, then delta S is the integral of dq over T. Now if you look at the surroundings, it's also the integral of dq over T, but with a negative sign. So this two may cancel. The entropy change of the universe is thus 0. Now why this equation? Again, we learned this. For the surroundings, any dq surroundings is considered a reversible dq surroundings, and dq surroundings is equal to negative dq, because we're assuming dq universe is always 0. There's no heat flows into the universe, there's no heat flows out of the universe. Therefore dq of the universe is 0. Therefore dq plus dq surroundings is always 0. And that's why I was replacing this dq reversible with negative dq, and then the result is expected. The change of the entropy of the universe is 0 for this reversible process. Again, we can express this as the second law of thermodynamics. Well, basically this says, well, the entropy of the universe cannot decrease. Now let's look at example problem 4.5.2. Let's prove delta S universe is positive when heat flow from the higher temperature surroundings to the lower temperature system. So heat flows into the system, Q is positive, and delta S of the system is Q over T cold. This is the temperature of the system. Now let's look at the surroundings. It's negative Q over T hot. Delta S universe is the sum of delta S of the system and delta S of the surroundings. So we need to add this up, and then Q is the common factor. Really, it's just 1 over T cold minus 1 over T hot, and then multiply by Q. Again, Q is positive because heat flows into the system. And let's take the difference here. This difference is also positive because T cold is less than T hot. So overall, delta S universe is greater than 0. Now, what if the system has a higher temperature? The surroundings has a lower temperature. Let's evaluate the entropy change of the universe. Same equation here. Again, the universe is simply the system plus its surroundings. And delta S is Q over T hot. T hot is the temperature of the system, and then T cold is the temperature of the surroundings. So we have this expression. We can combine this two because we have this Q is the amount of heat lost by the system, and this Q is also considered the amount of heat gained by the surroundings. But if you look at the sign of Q, Q is less than 0 because Q is defined to be the heat that flows into the system. In this problem, heat flows out of the system, and therefore Q is negative. Now let's look at the entropy change of the universe. It's the sum of these two. We'll take the common factor out. We're going to use negative Q here, and then it becomes 1 over T cold minus 1 over T hot. Negative Q is positive, and 1 over T cold minus 1 over T hot is also positive. And therefore, the entropy change of the universe is greater than 0. Again, in this example problem, heat flows from the surroundings to the system. In this example problem, heat flows from the system to the surroundings. Either way, the entropy change of the universe is greater than 0. The entropy change of the universe is greater than 0. But in these two cases, what's in common? What's in common? It is this: heat flows from a higher temperature object to a lower temperature object. Heat flows from a higher temperature object to a lower object temperature. So that means the heat flow from a higher temperature object to a lower temperature object is a spontaneous process which is associated with the entropy increase of the universe, and we cannot reverse it because the reversal would result in the violation to the second law. And another thing I want to mention is later we're going to see this delta S is greater than Q over T cold, and over here this delta S is greater than Q over T hot for this problem. So in the end, this delta S universe is greater than this expression, but of course this is greater than 0. So if you have this delta S universe greater than a positive number, so this is greater than 0, so it's going to be greater than a positive number, and therefore it has to be positive. Same here, this delta S universe is greater than this positive number, and this tells us the entropy of the universe increases.